Okay, so let's look at another example. So let's say I have another high-level function I want to implement. It returns a single integer and it takes 4 integer arguments. Inside this function, we can see the equation that we need to calculate, and we see that it also has at least one intermediate variable called f, where it stores the value before it returns it. So the parameter variables g, h, I, and j will be put into argument registers, a0 to a3, and we'll use the register s0 to hold the variable f. And we're going to assume that we also need one more temporary register which will store the value in s1. So because this function is using the registers s0 and s1, it's going to need to be careful to save the previous values, because the calling code, the main program that's calling this subroutine, may still have values that it needs in those registers. So where are the old register values saved in order to restore them after a function call? And as you can probably guess, the stack is an ideal place to put these saved values. And for RV32I, the register that has the address for the top of the stack, or the stack pointer, is typically stored in register x2, or the symbol SP. And as is the case with many machines, the stack starts at a high address and grows down. Okay, so let's look at the code for this subroutine leave. The first thing we're going to do is allocate 2 spots on our stack, 2 words, for those 2 saved registers. And we'll do that by subtracting 8 from the stack pointer. We can now push the data, the registers we need to save, S1 and S0, onto the stack. So we'll store S1 at the stack pointer plus 4, and then at the top of the stack, we're going to save S0. Now we can do the actual work on our function using S0 and S1 to hold our temporary results. And then the final result, which is our return value, will be put into register A0. And now that we've finished the work for the function and also set up the return value, now we can restore the registers from the stack. So we'll load back from the stack, the top of the stack, as 0, and then load from the stack pointer plus 4, the register S1. And then finally, we'll deallocate those 2 spots on the stack by adding 8. Notice that we're doing the operations in reverse that we did at the beginning of the function, when we push the values on the stack, and at the end we're popping them off. This sort of epilogue and prologue code for functions is very common for machines. The last thing that's going to happen, and is critical for the execution of our function, is to do the return, or the jump back to the value that was stored in the return address, the RA register. So before the function call, our stack pointer was pointing to the last value that was placed on the stack. As soon as we entered the subroutine and started executing the subroutine, the first thing that happened was that we allocated 2 words on the stack. We decremented the stack pointer by 8. Each word has 4 bytes. And then we stored S1 and S0 on the stack. We pushed those 2 values. And then after the call, the last thing that happened was that we popped the 2 values and then added 8 to the stack pointer, deallocated those values. Okay, a quick note here, and that the stack can also be used to save many other types of data. One specific example of this is that in C, there are 2 typical storage classes, automatic and static. Static variables are those that exist across different procedures, while automatic variables are those that are local to a function, and they're discarded when a function exits. So these local variables for functions, when not able to fit into registers, are typically stored onto the stack. And when putting all this together, for many machines, we call this the procedure frame or the activation record for a function. So before a function call, the stack pointer is pointing to the frame corresponding to the previous code or procedure frame. And then when we call the function, we're going to allocate a new frame. And machines have different ways of ordering this, but they typically have the saved registers, saved arguments, return addresses, and local variables. After the subroutine finishes, that frame is popped off the stack. Okay, so let's look at another example. So let's say we had a subroutine, which inside of that subroutine also called another subroutine. So this one called sum square calls a multiply function inside of it. So again, notice similar structure. Once we're inside the subroutine, we're pushing values onto the stack, and at the end we're popping them off. Because we're also calling another subroutine within this subroutine, and we're going to overwrite the return address register RA as well as the A1 register to pass the parameter into the multiply, we're going to need to save these onto the stack. And so this is what happens first. We're allocating 2 words by subtracting 8 from the stack pointer. We're storing the return address onto the stack, and we're also storing the argument A1. We then set the 2 arguments for the multiply subroutine, which are both x. So A0 and A1 both have the same value. And then we're going to go to the multiply subroutine. When the multiply returns, we'll have the result in the register A0. We're going to need to restore the value of A1, which had our value y that was passed into our sum square function. And so now we could add y plus the result of the multiplication, adding A0 and A1, and putting this into our return register, the A0 register. And then an important step before we finish is that we need to restore the return address for the sum square. Remember that at the beginning we pushed this on the stack as well, so now we're going to pop that off. And the last thing we'll do is we'll update the stack pointer so that it's in the right place when control returns back to the calling program. And then finally we'll do a return.